Okay, so let's compute the total hydrostatic force on the wall of a dam. So the simplest case is if we just have a rectangular wall, something like this. So let's say that the total length across is L, and then the total height is H. So this is a vertical wall, and on the other side of the wall is water. So we have some sort of dam that's holding back this large body of water. And we want to compute the total hydrostatic force acting on the wall. Okay, well, the pressure, so let's let x be the distance to the top because that makes sense. And then the pressure at depth x is just going to be rho g x. So it's the density of the water, which is 1,000 kilograms per cubic meter if it's water, times gravitational acceleration, 9.8 meters per second squared, times your depth in meters. So there's the pressure. Okay, so as we mentioned in the previous video, we're going to do slices. So we do a horizontal slice. And the reason for making a horizontal slice is because that the pressure is going to be the pressure everywhere along this slice is going to be the same because this slice is everything here is at the same depth below the ground, below the surface of the water. So everything's at depth x. So since pressure varies with depth, we get a constant pressure along this slice. So we can approximate the pressure as just rho gx. So we multiply pressure times the area of this rectangle to get the total force acting on that little slice. So the area of our slice is just going to be L times delta x. Right, because we have the length across is L. The length across is constant. This is why this is the easiest type of problem, because the length is just constant times the delta x, and you get L times delta x. So the total force acting on the slice, so I'll call that delta F because it's only the contribution of force to this little slice, so it's not the whole wall. Delta F is going to be approximately the area times the pressure. So it's going to be rho gl x delta x. Rho gx times Lx. The pressure times the area gives you the force. So the force acting on that horizontal strip is rho glx delta x. So therefore the total force is going to be approximately a sum I equals 1 to n of rho gl x sub I delta x. That's the Riemann sum. Of course, we take the limit as n goes to infinity, and this becomes a definite integral, and it becomes exact. So the total force is an integral from 0 to h of rho gl x dx. Now, when we integrate this, we get x squared over 2. Evaluate at h, it's rho gl h squared over 2. So that's the total force acting on this dam wall. So we have our dam. So the total force acting on the wall is rho gl h squared over 2. Now there's an interesting interpretation here. So L times h is the total area. So the total area is L times h. And so you can interpret this, you can break this out as follows. L times h times rho g h over 2. So the total force is the same as this. So it's the total area times the pressure exactly at half of the depth. So that if you look at the pressure just at h over 2, you can multiply the area times the pressure at that depth and get the same answer. Now this only works because there's a symmetry here. It only works because it's a rectangle. It won't work in other problems that are not rectangular because as the length L changes with depth, it's going to weight everything differently. So in other words, if you have some sort of plate that looks like this, the pressure at this depth has more of an effect than a pressure up here because it's longer, so there's going to be more area. So it's not going to be just the average height or the average depth times the total area. You can't do that in general. But for a rectangular plate, you happen to get that same answer, which is kind of a nice observation. Okay, so there's the rectangular plate, and let's do a trapezoid. So let's continue our merry way with a trapezoid. So we'll consider something like this. So this is supposed to be symmetric. So let's consider a dam that looks like this. So this is, and let's say we have 400 meters across the top. So we have a nice large dam, 300 meters across the bottom, and a total height of 200 meters. And we want to compute the total force. So if the other side is filled, there's water on the back side of the wall, what's the total force acting on this dam wall? So we want to, again, look at horizontal slices like this. So we're going to slice it up like that. And so this time, and of course, we want to have x being measured from the top. So that's right at the surface, so that the pressure at x is just rho gx. Okay, so this time we have a length that varies with x because it's longer up top and shorter down here. Now for triangles and trapezoids, the length will vary linearly because these are basically linear shapes, right? The length is just changing linearly. So let's look at the length at our different depths. So at a depth of x is equal to 0 versus a depth at x is equal to 200. So we want to find L of x. So L of x is just the length across as a function of the depth. So we know that L of 0 has to be 400 and L of 200 has to equal 300. So we're basically connecting of a linear function that has a total length across of 400 at the top and a total length across of 300 at the bottom, at which point the depth is 200 meters. Well, the first data point gives us our y-intercept. The y-intercept is 400. So if we think of L of x as a linear function, now it's decreasing, and when x changes by 200, the length it drops by 100. So it should be minus 1/2 x. So when x is equal to 200, we get 200 over 2, which is minus 100, so we get 300. You could also just do this like a slope, like 300 minus 400 over 200 minus 0 gives you minus 1/2. It's supposed to be a 1 up there. Doesn't even look close. Minus 1/2. So the length across is 400 minus 1/2 x. And there are a variety of other ways. I mean, you can, be more geometrical approach, but that's kind of the simplest way. Whenever you have a trapezoid or a rectangle, just fit a linear function to your two data points. The length across has to be 400 when x is equal to 0, and the length across has to be 300 when x is equal to 200. So what linear function passes through 0, 400, and 200, 300? So when x is equal to 0, depth is 0, length is 400. When depth is 200, length is 300. What linear function matches that? Do it any way you want for finding linear functions. Okay, so that's our length across. And so therefore the area, so the delta A for our slice is the length times the delta x. So this gives us 400 minus 0.5x times the delta x. Now if we integrate this from 0 to 200, we get the area of a trapezoid. You can check that on your own. So the total force acting on the slice is going to be area times the pressure, rho gx, 400 minus 0.5x delta x. So the total force is going to equal rho g times the integral from 0 to 200, 400x minus 0.5 x squared dx. Here I factored in the x. We get 400x minus 1/2 x squared. Rho g for SI units is 9,800. For water, density of water is 1,000 kilograms per cubic meter. So rho, we take 1,000 kilograms per cubic meter, and g is 9.8 meters per second squared. So we get 9,800, whatever the units are here, and then 400x squared over 2 becomes 200x squared minus 1/2 x cubed over 3 becomes x cubed over 6, evaluating from x equals 0 to x is equal to 200, so we just have to plug in x is equal to 200. So we actually get 200 cubed on the first thing minus 1/6 200 cubed. So this is 9,800 times 5/6 times 200 cubed. So let's see what we get there. 5/6 times 9800 times 200 cubed, approximately 6.533 times 10 to the 10 newtons. So that's about 65 billion newtons of force acting on that wall at any given time. So this is how you use the idea of slicing and integration to compute hydrostatic force problems.